My name is Steve Sanford. Some of you may know me from last March, I believe, when I came and spoke. And what we're going to do for the next 5 weeks is a little bit of a continuation of what we started back then. I came and spoke about the history of the space program with an emphasis on the national benefits that we accrued from undertaking that great adventure. Even going back to 1917 and the beginning of aeronautics in this country, at least aeronautics research. And so what we're going to do over the next 5 weeks is give you a much more detail about what's going on now and what NASA is planning and how we intend to take the next steps into deep space. Today, we've got Pat Troutman and Dan Masnick here. They are two of NASA's leading space architects and have been intimately involved in the agency working with centers across the country and planning the best way to move into deep space, building on what we've done in the past and on the capabilities of the International Space Station that we have up there now. And I'm going to turn it over now to Dan and Pat and let them take it away.
Okay.
Thanks, Steve. Sound check. Can everyone hear me okay?
How about me? Good? Okay. All right. Well, welcome, and thank you for coming out this morning. We appreciate you coming. What we're going to do is we're going to talk about a future history of human space settlement. So now this is a history. We're going to tell you how this might take form. And what I'm going to first do, we're going to talk about the first steps, the asteroid redirect mission and the path to Mars. But before that, I'm going to take you a little bit farther into the future. So I want you to, and first there's a disclaimer here, in that this presentation is meant to educate and evoke discussion. So at the end, hopefully you have some questions, and we'll be able to answer those for you. It doesn't entirely represent the official position of NASA. There's plenty of official information, projects that we're working on. But certainly this introduction is fictional. And I want to take you, imagine for a moment that you're in a history class in the year 2776. And you're in a high school at First Colony High School on the planet Nova. So this is our history. About 800 years ago, our ancestors here on Earth, they had the forethought, the economic fortitude, and the know-how to take the first steps in spreading out from the Earth. And this is our new home, Nova. We've been here 100 years. It was originally discovered on November 21st, 2012. Now that's in Earth years. And we've been here 100 years since our first settlers landed. And that's about 8 Earth years. Soon after we arrived, all Earth transmissions ceased. After we suspect, because of the transmissions, viruses released from biological warfare spread through the solar system. Here's a picture of the sunset on Nova, and you can see it's a triple star system. Nova orbits Gliese 667c, and it has 2 twin stars. Nova, as we've called it, is a super-Earth. It's about 4.5 times the mass of the Earth. So the gravity is a little more substantial for the colonists than we experience here on Earth. And it orbits its parent star every 28 days, so pretty much the orbit of the moon around the Earth. It's located 22 light years away from the Earth, so that's about 1.4 million astronomical units. An astronomical unit is the distance between the Earth and the Sun. So it's a little bit of a haul to get out there. So how we got here. 3 generations traveled in 12 artificial space arcs and devoted their lives to the journey to the Gliese system. So you think about it, it's 22 light years away. It's even if we can obtain a fraction, 1/10 of the speed of light, which maybe we can someday in the future, it's a multi-generational trip. So we had over 7,000 colonists at first departure. Of course, many more were born and many passed away during that time. More importantly, we housed all the terrestrial life forms that could be transported. So it wasn't just taking a colonist and going to a strange new world. We brought what we could with us. It was constructed in the Jovian system out of materials processed from asteroids and the moons of Jupiter. It utilized advanced fusion propulsion using helium-3 and hydrogen extracted from Jupiter's atmosphere. And the colonists left in the year 2560. So the journey took a little over 200 years to make. So we asked the question, that sets the stage, why should humans explore space? Certainly, we live on a big spaceship. We're constantly going around the sun every 365 and a quarter days. We're in this spaceship, and we're in a single spaceship right now. We have a multitude of things that we need to be concerned about, just hazards in the solar system. One of them is comets and asteroids. And I'm sure most of you probably are aware of this, but we kind of call it cosmic shooting gallery. This is just the leftovers from the creation of the solar system. And it's not that these asteroids and comets have any ill intent. It's just they're orbiting with us, and every once in a while, they run into us. As a matter of fact, we had a very close approach this last week of a very small object, about 40 feet across, that came by 2014 CR, came just outside of our geosynchronous satellite orbits. But it's a constant reminder that we have threats that come in from outer space that we have to worry about. So we have to worry about ourselves and what we experience outside. This next animation depicts what the final state of our sun will be, a red giant, and how it will eventually consume pretty much out to the Martian orbit. Our sun's going to expand. Now, all estimates are this will be 4 billion years or so from now, so we have nothing to worry about from that standpoint. But someday we will have to leave, and when we start out, we're talking about making those baby steps to begin that process.
Point here, Dan, is yesterday there was a major solar storm with a coronal mass ejection. It's heading towards Earth. It's going to hit tomorrow sometime. People as far south as Michigan might be able to see the northern lights. You might hear some stories of disrupted radio transmission and power grid outages. That's just a small sample of what could happen. Back in 1869,
65, the Carrington event.
The Carrington event wiped out what was the major telegraph infrastructure of the United States at that particular time. So it's not just end-of-life things we have to worry about. We have to worry about the solar system throwing things at us constantly. And civilizations is a very fragile state sometimes. It only takes a short little push one way or another to get us to the point where we cannot actually sustain going into space. It's not that it wipes out humanity. It removes our ability to spread humanity's seed. So just a thought.
Yeah, and to follow that up, the Carrington event, it was such a strong solar storm that railroad tracks actually ignited because they acted to conduct the energy, the particles that came in. And of course, the wood and the tar and all the ignitable things actually caught on fire. If we had a similar circumstance like that, as Pat mentioned, it would affect society. The question is we've reached this point in history of humankind that we actually can contemplate our place in the universe, and we can actually go out. We've proven that we can go to the moon. I mean, we know that we can explore beyond the moon, and Pat's and I are going to talk about that. But what if the clock got reset? What if we did have something happen where we were sent back to the Stone Age? Would we ever be able to recover back to the point we are? So it's interesting to think. I like saying to folks to ponder that the telescope and the rocket, in the final analysis, may be the two most important inventions in all of human history because, for example, for comets and asteroids, first of all, we have to be able to see them. We have to be able to know where they are. And, of course, we have to get to them before they get to us if we want to do something about it. Similarly, if we want to find an Earth-like planet in another solar system, and we're doing it right now, we need telescopes, very sensitive telescopes, to be able to see those. And, of course, if we want to get there, we need a rocket. It's going to be a different rocket than we're thinking of today, but we need the propulsion to be able to span the gulf of interstellar space. So, in some sense, if we as humans become compromised, I'll say extinct, because species go extinct over the periods of millions of years. But if we don't have the either extinction or the capability to travel into space at some point in the future, we're kind of stewards of all the life here on Earth. So it's something to think about, that we have that kind of that responsibility, and we've been blessed with the tools to be able to do something. So with that, I'm going to let Pat take over, and we're going to pull you back to a human history, a more recent history of space travel.
Yes, now you're in Ancient Human History 101. And since I'm the oldest, I get to preach that, since Dan and I are actually talking about, do you remember the Apollo lunar landing? And, well, he was 2.5. He actually remembers it when it happened. I was 8. I actually remembered when it happened. And it both involves a grainy black and white TV sitting someplace. And so you go back, that's the dawn of human expanding their seed. And Apollo was special in so many reasons. First was because the tremendous amount of capabilities we developed and the leaps in engineering and technology that were accomplished in that time frame. Just phenomenal. We have never duplicated that since. And there are reasons for that. Now, everyone says, well, it's because we were in a race with the Russians or we had infinite money. There's other things, too, that allowed that to happen. And that's reflected very much in things like you see SpaceX now, who's building rockets and making great progress and doing great things. They have a very young, fresh workforce. And believe it or not, back in the Apollo days, NASA workforce was young 20-somethings stewarded by some senior folks, and they worked 80-hour weeks. They lived, ate, and breathed it. And by the time we landed on the moon, we were spent. The NASA divorce rate was incredibly higher than everyone else's. We were on a war footing with that. We wanted to achieve that what had never been achieved before. We wanted to beat the Russians, and we dedicated everything we had to do it. And we ran the whole marathon at full speed. When we got to the end of Apollo, the country was a little tired. Yeah, been there, done that. The workforce was just expired. And actually, we didn't actually know what we wanted to do after we got to the moon. We were running so fast, we forgot about the rest of the journey. So Apollo taught us a lot of things. And of course, at the dawn of the Apollo era, NASA was not a bureaucracy. It was a young, agile organization that didn't care about sustaining itself for long periods of time. By the time it reached the end of Apollo, NASA was a full-up bureaucracy, and we still are today. So I'm not making excuses. I'm just saying that's the way it is, because throughout the history of space exploration, going from Apollo to 800 years in the future, bureaucracy and political momentum and budgets all play a factor into how we have to accommodate and how we have to plan for the future. So it's not nice. It's more easy. I want to talk about rockets and warp drive and all this great stuff. That's only half the problem. It's getting people, stakeholders, congressmen to understand that this is worth doing and to give up something old in order to do something new. And you'll see this repeatedly happen through history. So I'm going to tell you a little about it. So Apollo, great, wonderful thing. After Apollo, we got there, and as I said, what are we going to do? Well, we had some leftover rockets. We just spent 10 years beating the Russians. We said, well, maybe you ought to start making good with the Russians. And so you see this idea of reusing what we got, making it do something else, and doing it in a way with international partners to help get that political stakeholders that we don't have with just the mission alone. So by involving other countries who also want to invest in their space program and give it a reason for being, it just adds another reason to go do it. So you'll see this theme where we take hardware, we reinvent it a little bit, apply it to something else, and then we go do it with the internationals because, hey, if their Congress wants to do it and our Congress wants to do it, then maybe we'll get funded to do it. So the Apollo-Soyuz program was it was bringing a module, uniting the two programs. Instead of running against each other, we were shaking hands. After that came the space shuttle. And what was really interesting is the space shuttle was, well, now we're going to completely change our mindset. We're going to do a total reusable system. We're going to launch hundreds of times a year. We're going to enable this whole industry in space, and it'll just take care of itself. That's how shuttle was sold. It didn't really turn out that way. It was an amazing engineering feat. In fact, much more so than the Saturn V rocket. because there were miles of wires and circuits and stuff and tens of thousands and millions of parts on this thing, and they all worked. Yes, we had some setbacks and some tragedies, but the fact that this system could go up, go to space, go up there for weeks at a time, come back, be refurbished and reused, it really was something. But then we had Challenger, we've had Columbia, and the role of Space Shuttle was muddied a little bit. It was going to be this reusable truck that takes satellites and everything back and forth. But then we didn't want to jeopardize people's lives in delivering cargo, so we had a separation of crew and cargo, and Space Shuttle was only to be used for human missions. So we had to have a lot of human missions to use the Space Shuttle for. We looked across the seas to our friends, the Russians, and we said, "You've got a space station. We got a truck. Let's get together." And we did. That was the Shuttle Mir program. So I was fortunate actually to be on the beginning part of that particular program, where we went over the Russians and we negotiated and we set up a series of protocols. And sure enough, they had launched their space station. We were flying back and forth. We were getting experience. And now everyone's happy that we were working with our friends. It was an international experience. And we were learning how to operate in space on Mir. But then we did that a bunch. And it's like, well, what's next? Well, Mir was coming to the end of its lifetime. And so we built the International Space Station. So I'm going to talk about that a little bit. But right now where we're at, the Space Shuttle is retired, International Space Station is operational. What are the next steps that we're going to do? What is our journey to 800 years of the future? I forgot the name of the planet. What's it? Nova. Nova. Okay, I can remember that one. Nova. Dan and I carpool every day back and forth to Williamsburg. And so we discuss this as we carpool. And then our offices are across the hall from each other. And then he goes to all his meetings all day. I'll go to all mine. Then we get back in the carpool and we discuss it. So this is how we integrated this thing together. So as I mentioned, politics is an important part. Every new president that comes into office says, well, NASA now works for me. I'm going to tell NASA what to go do. And what's very interesting is that sometimes the presidents have different implementations, but their higher level themes are very close. This happens to be a statement by President Obama. And the points I want to point out here is, our goal is the capacity for people to work and learn and operate and live safely beyond Earth for extended periods of time, ultimately in ways that are more sustainable and even indefinite. That is the path for extending human presence. Now, what's really funny is that 8 years beforehand, George Bush came out with the vision for space exploration, and he said the exact same thing. But then the spin masters came in, and they took George Bush's thing and said, oh, that means we're going to go to the moon. And then when Obama came in, the spin masters came in and said, we've already been to the moon. Let's go to an asteroid. And so we lose sight of the long-term goal of extending our seed and learning to work in space by these short-term goals of, well, by the time my administration is done, we're going to go do this, so I can hang it on my wall and say, I allowed NASA to go to an asteroid or go to the moon. You need short-term projects, deadlines, in order to focus. The problem is that what you have to invest in to go to the moon may not be the same what you have to invest in to go to an asteroid. They're different things. So NASA does this game where we sort of do the hula as we're trying to adapt to the current administration. So our strategy is something now called the Evolve on Mars campaign, where we're focused on creating infrastructure, capabilities, a logical path that it doesn't matter if whatever the next president is, doesn't matter if it's from a red state or a blue state. When he comes in, 95% of that work and effort we've done is not going to have to get redirected and refocused. So our goal is very much, as the presidents have said, doesn't matter whether it's Bush or Obama, define the pioneering strategy for extending human access and operational capabilities in the journey towards the Mars system. So there's our, as Steve mentioned, our horizon goal. So we want to focus on going towards Mars, because whether we go to the moon, whether we go to an asteroid, that's the next hump. So it gets us across that specifying certain things to go to a certain destination. So we're laying this foundation for going to explore. So it doesn't really say that we're gonna land on Mars at this particular time. You saw Mars vicinity in the 2030s. Mars vicinity can be interpreted as going to the moons of Mars, it can be go to the surface, it can mean just going in orbit. The president did later come on and say, after he talked about extending human presence, he said, well, and by the way, I want humans to go to an asteroid in 2025. So he had to have his own particular date. So that immediately became Dan's headache. So we'll talk about that. So my headache is Mars, his headache is asteroids, and we have to figure out how to weave a thread between those two, because we don't want to invest in one that doesn't enable the other. So we're all on the same page, no matter what we do. These particular things are the guiding philosophies. Bottom line is, it needs to make sense. It needs to get to a point where we're not dependent on Earth, and it's got to start off within budgets and grow to something based upon projected future NASA budgets. So this is not a plan, this is a philosophy. So it sort of looks like this. There on the left is the International Space Station. That's where we're at today. It's complete for the most part. 30, 40 shuttle flights to assemble and put that together. Nations across the world, including Russia, who owns half the space station. They've made some comments recently about, well, 2017, we're just going to break our part off and fly away. See you guys. There's pros and cons to working with the internationals, because relationships can change, as we're sort of seeing in the world stage right now, and we have to adapt to that. So even though we want to include an international perspective in everything we do, we still need a fallback plan if key partners go away. So that's part of the strategy we're putting in here. So you see these bubbles. The big bubbles, International Space Station, something here in the middle of the chart called a proving ground, that's the lower center of the chart, and then bubbles for the Mars moons and to the surface of Mars. Each time we go through those is a large capability investment. Billions of dollars to make the next step happen. So it sort of looks like this. In low Earth orbit, space station is there to answer a couple questions. It was initially put there to say, can international communities work together to do a space-based engineering project of a scale never seen before? And the answer was yes. We could figure out, put together, take everyone's parts, they fit in space, and they all worked. Much more successful than a lot of us thought. That was my first project coming to NASA, was International Space Station. And through 20 years, it went from notion to operational to being finished. And now it's my job to figure out what to do with it afterwards. So the first part was engineering and operating. The next part is, how do we use that as a test platform so people, to understand if people can survive for years in space. And in space, there's no gravity. No one can hear you scream, and there's radiation. So we have to test those things on space station. So it's an ideal platform for doing that. So all these zero-G human factors, long-duration systems, high-reliable systems, that's what space station is going to prove at. The point is, though, is when we prove those out on space station, in order for us to go on to the next destination, space station should go away. Now, what happens with bureaucracies and institutions? What is their main goal in life? Survival, to sustain themselves. So we have a space station. 10 years, we could be finished with everything we need to do on that. Nothing more. All the research will be done. We can move on to the next target. Space station doesn't want that. The congressional delegation in Texas and Alabama, they don't want that because there are jobs now that are running. So this is the dilemma we face. We can't move on to the next step unless we can reduce investments in current things. So it's a challenge that we're always fighting. But to get to that next step, to get beyond low Earth orbit, you hear what Steve talked about, investments in major transportation functions. That is the Space Launch System. That is the Orion space capsule. That is what Dan's going to talk about, solar electric propulsion to get you into deep space efficiently. Space station was billions and billions of dollars. Space Launch System, Orion, high power in space propulsion, billions and billions of dollars. How do we pay for these extra things? Now, what did we just decommission? Space shuttle. So those funds in the NASA budget used to pay for space shuttle. Now we're reprogramming to pay for SLS, Orion, and hopefully the Asteroid mission. So that's where that box is being paid for. But if space station doesn't go away, how do we get to this next box on the right, which is the Phobos-Deimos Mars orbit? This is where we go from, On space station, we're 1 day away from the surface of Earth. We just hop in a Soyuz, not an American vehicle, a Russian vehicle, because we have no American vehicle that gets back and forth to space station now. We hop in the Russian vehicle, get back to the surface. When we're in what we call the cislunar space, this area here, where SLS and Orion will be able to take us to, that's days to weeks away. Not bad. Our current systems on space station are fully sufficient to keep the crew surviving. When we start talking about years away from Earth and years away from coming back, which we're talking about in the Mars system or going to asteroids themselves in their native orbits, we have a whole new class of systems. So we're on space station where we can order up spare parts, every few months. They come up on the Russian or the SpaceX or the orbital delivery systems. We can't do that when we're deep space. So things have to be more reliable. Spare parts have to be common and unique, and we're not there yet. Systems have to last long, and then we have to get to this next level of propulsion, hundreds of kilowatts of power pushing the spacecraft out to deep space. So it's like a billion or so, but a couple of billions. It's not tens of billions, it's billions to get out there. But when you see going to the Mars surface, that is a huge set of investments. As Steve said, we don't know how to get people down there yet. So these little boxes you see on this page, we'll be hanging there for a while. So the next box we'll be hanging at will be this one here at cislunar space. Space station, I just talked this whole chart basically. We have to adjust space station so we can answer those questions about how people survive long duration flights. We need to increase the duration of crew going to space station. Right now they go 180 days, they come down. That way all the astronauts from all the countries get to fly to space station. That's not telling us anymore what we need about to go to Mars. We need to have them up there for 1 year, 2 years, see what happens in this environment. So again, it's getting the culture to accept the fact that we need to go do that. And as I mentioned, we can't go to space station right now unless we buy a Russian ticket. There's some place in between that if this geomagnetic storm that's coming tomorrow could be a destination of very much interest, and it's geostationary orbit. Those satellites up there, they give us when I give this lecture to teenagers, it horrifies them. I say, one bad solar storm, it's going to knock out your DirecTV, your cell phone, your GPS, and your texting. And they go, oh, my daughter's going, oh no, that's terrible. So from a taxpayer perspective, we need to guard and be able to get to geostationary orbit. Right now, it's not a destination because it's seen as routine. But if we were to lose one satellite and it were to break apart in geostationary orbit, it can ripple and take out all the satellites. So the ability of sending people and robots to geostationary orbit to repair spacecraft is a very important thing. And it's in the back of our mind. So when you see NASA talking about going to the moon or Mars, we're also building systems to go rescue our basic infrastructure in geostationary orbit. It's just not glamorous and sexy, but it is very important. Next step along the way, going towards NOVA, is what we call Lagrange points. This is the place where the Space Launch System and Orion can actually get to without additional investments in transportation. And these are the far side of the moon, lunar orbit, places like this. And this is where we get exposure to the deep space environment. Low Earth orbit, we're protected by the Earth's magnetic shield, at least until the solar flux hits. And we're still protected, but not as much. And then by having systems out in deep space, we'll expose them to this radiation that Steve was talking about and understand the implications on human-rated systems for long durations. And there's other activities we can do here, like teleoperating robots on the surface of the moon, laying the ground for people eventually to go there. Sample return, where humans actually bring back the samples. Right now, this is where we're going to get to with our current investment. This is that next box we were talking about there. So we're talking about a lot of activities that go to this position, and Dan's going to talk to you about the asteroid redirect mission that takes advantage of this place too, where it also comes together in a reasonable place. The moon, yes, we've been there, done that. Prior to the last administration change, that was our destination, as I mentioned before, and we worked very hard with the internationals to come up with an integrated strategy where we're all doing the same thing. We were singing Kumbaya, and we're going to go off to the moon and explore it in a way, not that was like Apollo, but in a way that laid the groundwork for sustained presence, like we're talking about with Mars and NOVA and these other places. Again, Next president came in, they changed the destination to an asteroid, and this sort of fell along the way. But going to the moon would give us all that experience with long duration, low gravity systems and a dusty surface. And if we don't do that at the moon, when we get to Mars, we'll be trying it for the first time there. So the moon is still very important in moving out into the solar system. Near-Earth asteroid. So I'm not the one to be talking about this, Dan is, because this is his passion. He's been working near-Earth asteroids, comet asteroid, protection schemes for his whole career. But it's part of my job too, in that they represent a good segue between what I'm calling the cislunar space and actually getting into Mars. The problem about near-Earth asteroids is that each asteroid itself has a predictable, repeatable orbit, but we don't have opportunities every 2 years like Mars, or we can't go every day of the week like we can to the moon. So if you miss a window for an asteroid, you got to go find another one. So it's hard to plan human missions decades out to an unknown particular target. And again, Dan's going to talk more about that in his robotic
There's
mission.
lots of asteroids out there.
There's lots of, they're always coming along, but so the thing about the asteroid missions is that everything you need for an asteroid mission, you need just a little bit more to do Mars. So it's a great stepping stone, but it's only a 1-year mission at most compared to 3-year missions like we're talking for Mars. So a great next step beyond cislunar space. Now, when the president came out, the last president came out and said, "You go to an asteroid?" We said, "Yes, sir. We're going to go plan an asteroid mission for you." And he didn't say, "Well, I'm going to give you a budget increase to go do this." So we said, "Okay, what would be an interesting target in the late 2020 timeframe?" And there's this asteroid called Apophis that's on its way. So I'm just going to let this play, let you watch it, enjoy it, and then I'll tell you a little about it later.
Dave, an extraordinary television picture here. Okay, extraordinary television. Okay, Houston, as I stand out here in Bird was on time. Price is really striking. -1, 6% fuel. 10 feet, -1. Houston, we have capture. This is really a rock and roll ride, isn't it? Today, Charles, sunlit, isn't that beautiful? Really is. Hello, Houston. On the way home. Roger, down. Stand by. We're free. Good. Down here, we're free.
So we came up with an asteroid mission. Then we costed it. Now, we can't afford to do that. And it's very important. Why an asteroid mission? Of course, we talked about the whole planetary defense nature, and, the asteroids have shaped our past and they will shape our future. Asteroids offer a vast potential of in-space resources that allow us to sustainably explore the solar system. This particular one, as you saw, is going to come by very close, and then it's going to pass through a gravitational keyhole. If it were coming and it passes the wrong way, it could come closer. Right now, they don't think it's going to hit. But you would want to put a tracking device on there. You would want to put remote telemetry on there. You want to put a science station on there. You want to understand your enemy. So intelligence is very important. So if you had to go on an asteroid, resources, planetary defense are big reasons to go there. But the problem we had is that back in 2009 when we did that, the budget wasn't there to do that mission because we had to bring all those systems further in time into about 2028. We had to have the long duration habitats and years in space. We were close, but we weren't right back there. So this particular mode, we sent a crew to the asteroid in its native orbit. And the one day, Dan was at a meeting out at JPL, and they were talking about, well, what if we just bring the asteroid back to the humans and meet them halfway? And hence was born Dan's job. And so he's going to tell you about that now.
Okay. So Pat said asteroids and comets are my passion. I don't know, a little passion may have rubbed off a little bit on Pat here and all our carpooling. So I'm going to talk about what I really think is the key. We talked about what motivates us to leave the Earth, right? And in simplest terms, there's a difference between exploration and settlement, or you can call it colonization. Some people don't like that word, but staying. When we go out and anything we do, you go explore something, there's got to be a reason to stay, right? You explore, okay, that's great, and you go home. But if you go and there's stuff there, there's things that you can do, there is economic potential, that's when you stay. And that's been the history of mankind in terms of exploration. So that is really the key. And part of the motivation was the ability to get to an asteroid and having the funding and be able to make those steps out into deeper space. But another big part of what I'm going to talk about is the potential for resources and how those resources can be harnessed to help us explore space, as well as potentially return to terrestrial markets. And I personally think that when you start talking about economic expansion, we're all driven by that, whatever society we are here on Earth, we like our stuff. We need stuff. We need food, we need shelter, we need clothing, and we like all the things that come along with that, or come along as entertainment and travel and all that. But you have to have what I call an economic backfill. If we go out in space, there has to be an import back to the Earth, an export from that location. So I'm going to talk a little bit about NASA's Asteroid Initiative, and part of it is to combine the aspects of planetary defense, and these represent natural hazards just like hurricanes or earthquakes, but we actually can know about them and actually do something about them. And also the Asteroid Redirect mission, and I'll explain what that is in a moment. But basically, we've adopted this grand challenge within NASA to find all the asteroid threats to human populations and to know what to do about them. And I think that's actually pretty remarkable. Like Pat said, I've been interested in working this problem pretty much my entire career at NASA. I started off at the space station as well and worked on some other projects. But in my undergraduate work at Virginia Tech, I became very interested in this process of impacts and mass extinctions and the potential for, bad things to happen because of stuff coming to us. So that's a huge jump or a consciousness shift that I think has happened within the population, because we understand it, and within NASA. So I'm going to talk here about the asteroid redirect mission, and there's basically 3 components. There's an identify component, where we have to find objects, characterize them, and know what they're all about. And as Pat mentioned, they go around the sun just like the other planets, and sometimes they're in good positions, sometimes they're in not so good positions. But it's the same characterization that helps us find those that are a hazard, that might be a problem for the Earth. Then the second part is what we call the robotic redirect portion. And that's where we use advanced propulsion technology, in particular solar electric propulsion. And it has a very high specific impulse, or ISP. You might have heard that term. It's basically the gas mileage that you get out of your space vehicle. So it's very low thrust, but it can move, for every pound or every kilogram of propellant that you bring, you can get a lot of momentum transfer. So you can move large objects, be it slowly, kind of like a tugboat. But we've got 2 options. One is to find, characterize, and capture an entire small asteroid, kind of on the level that kind of came by, somewhere around 4 to 10 meters, the one that came by this past weekend. Something that's not a threat to the Earth. We actually have, the Earth's really cool. We have a couple force fields. First of all, we have our atmosphere that stops a lot of stuff from coming in. And every comet, every meteor shower that you see during the year, you go out and watch the shooting stars, that's our atmosphere stopping these little pebble-sized, pea-sized grains from coming in. Sometimes we have bigger stuff, the size of softballs or footballs or even a car or a house every once in a while, and they burn up in the upper atmosphere. So we're talking about bringing back an entire small one, or we have a second option that we call option B, of going to a large asteroid and capturing a boulder and bringing it back off the surface, a multi-ton boulder. And then finally, the third part is to explore this return material, and we're going to bring it to what we call lunar distant retrograde orbit. Right now we're looking at something that's about 70,000 kilometers from the moon. The moon's about 400,000 kilometers away from the Earth, so it's on the moon side, and it's in a stable orbit so that it will stay there for hundreds or thousands of years. But we're going to use the SLS and Orion to send crew members out to it to do the first initial exploration. I like to call it first contact, because if we have the resources and we expend the energy to bring this material, this asteroid material back, and if we bring the right kind of material, we can start looking at how we can process it for resources, including water, metals, radiation shielding, to start to look at some of these issues that we have in space. But I like to call it first contact, because if we're going to take that effort, I hope there's a lot more missions to this returned asteroid material that we'll do. In a nutshell, the objectives of this mission are to prepare for human exploration of Mars, as Pat mentioned, our Horizon destination, demonstrate advanced solar propulsion, enhance the detection, tracking, and characterization to defend our home planet. So those are a good thing there. And then also we're planning on demonstrating basic planetary defense techniques while we're at the asteroid. If we go to a large asteroid, then it's a very relevant, it's on a relevant size, something that could be a threat. And if we go to a smaller one, we can see the effects of that planetary defense maneuver faster because it's less massive, and we can extend that to larger asteroids in the future, potentially. And then finally, we've adopted another objective that we want to know more about these celestial bodies for scientific knowledge, and what we can know about resources to enable the mining of these assets in the future. And there's a couple companies that have set up in the United States planetary resources and deep space industries with the goal of characterizing and mining and one day returning materials to the Earth. So I'm going to this is a video.
NASA is developing the first ever mission to identify, capture, and redirect a small asteroid or piece of a large asteroid to orbit the Moon, then send astronauts to visit it and collect samples in the 2020s. Using telescopes in space and on Earth, NASA and citizen astronomers are studying the thousands of near-Earth objects around us, including good candidates for the Asteroid Redirect mission and hazardous ones we want to track. The robotic capture mission will prove a number of the capabilities humans will need to reach Mars in the 2030s, including advanced solar electric propulsion, an efficient way to move larger cargo payloads into deep space. NASA is studying 2 robotic concepts to capture an asteroid. The first concept would fully enclose a small asteroid in an inflatable mechanism. The second would use robotic arms to retrieve a boulder from the surface of a much larger asteroid. Each concept also provides opportunities to demonstrate techniques to alter the course of large objects in deep space, a capability that could help us defend Earth from impacts in the future. After capturing an asteroid, the robotic spacecraft will move it to a stable orbit around the Moon, where it could remain for hundreds of years. The asteroid will be so small that even if it did approach the Earth, it would burn up in the atmosphere and disintegrate before it could reach the surface. In the 2020s, astronauts aboard an Orion spacecraft and Space Launch System rocket will launch toward lunar orbit, gaining a boost in speed from the Moon's gravity to rendezvous with the asteroid. The journey will be the farthest humans have ever traveled into deep space. Orion will dock with the robotic spacecraft carrying the asteroid. Astronauts will conduct spacewalks to collect samples of the asteroid that could hold clues to the origins of our solar system and life on Earth. The crew will return home aboard Orion, having ushered in a new era of human spaceflight and scientific research. Groundbreaking work is underway to prepare for these human missions to deep space. This year, NASA will conduct the first uncrewed flight test of Orion. Aboard the International Space Station, NASA and its international partners are learning how humans can live and work in space for long periods. Astronauts on Earth are using underwater environments to test spacesuits, tools, and techniques they'll need to explore an asteroid. The lessons we learn and new technologies we prove through the Asteroid Redirect mission will put humans one giant leap closer to Mars.
So you can see in that last image, that's actually using the Asteroid Redirect vehicle to use the technologies that we've developed to head to the Martian system. So I think that animation that video does a nice job of kind of pulling everything together. She said a lot of things I said, so she repeated in there. But again, these are the 2 mission concepts: capture a small asteroid or a robotic boulder capture. And again, if we use Phobos or Deimos as a gateway to the surface of Mars, they're either very large captured asteroids. They may have come off of the Martian surface from a collision. Their origin is still being debated among scientists. But one way or another, they're a proxy for asteroids. So as we move out and we understand how to interact with asteroids, we send humans to asteroids. If we use the Martian moons, we'll gain a lot of knowledge there and information. I'm going to kind of skip this a little bit, but I'll just say that we have currently known candidates for both options. Several small objects, and then we have objects that we've sent robotic precursor. One asteroid, Itokawa, which this is a 3,000 scale model of Itokawa. So you're talking about 4 or 5 football fields in dimensions. This is about 500 meters across, and Apophis that you saw in that video is about 325 meters across. So these are very large bodies. We've also got 2008 EV5 and Bennu. This is a model of 2008 EV5 to the same scale. And this is one of the potential targets for the option B. And we've got OSIRIS-REx and Hayabusa-2 both traveling to large asteroids to give us reconnaissance for that mission. You can kind of see here, this just gives you a relative scale. There's Itokawa. There's the Asteroid Redirect robotic vehicle. And in terms of how much we can bring back, we potentially can bring back with option A up to 500 to 1,000 tons of material, given the right asteroid. We can do that with option B as well, but we have to contend with pulling it off the surface. So right now we're looking at something that's probably about 50 tons. Well, if you compare that to what we returned so far from any location, it's pretty it's pretty outstanding. It's just kind of mind-boggling to think we might be moving around 50, 20, even 25 tons of material. It just so happens those are the same types of masses that we need to move around, like habitats and landers and things like that. So there's the applicability of using the CEP spacecraft, the ARV, as a space tug. And of course, this just makes the point that if you go to a metallic asteroid versus a stony asteroid or a carbonaceous target, the densities are different, so the size relates to a different mass. Styrofoam ball versus a bowling ball. Size and density really matter. And of course, the carbonaceous objects, they may have up to 20% water contained in them, locked in hydrated minerals that you can extract and process. This is just a comparison of the ARV to a human. To give you an idea of the solar arrays we're talking about, it's a 50 kilowatt CEP, which is an order of magnitude larger than anything that we have commercially flying in geostationary orbit. So we're pushing the technologies there. It's about a half a football field for this upper configuration, which we call the ROSA arrays, the rollout solar arrays, and the Megaflex, which are kind of a Chinese fan type deployment, is shown in the bottom. But it's a large spacecraft when you put the solar arrays out fully extended. We're doing solar array technology work in 2014. There's examples of both of those technologies with humans in the scale, so you can see how large they are. It's big. It's definitely not as large as a space station, but it's still a large spacecraft. Working on electric propulsion, and this is really the key. We could not contemplate doing this with chemical propulsion, meaning like liquid hydrogen, liquid oxygen rockets, things that power the space shuttle and the Apollo. This is really a new technology that's been demonstrated. We actually have, Dawn is going to visit, it's visited Vesta. It's a robotic spacecraft, and it's on its way to Ceres, which used to be an asteroid. It's now a dwarf planet like Pluto. So Pluto got demoted and Ceres got elevated. But there may be an ice sheet maybe 100 kilometers thick on Ceres. And someday it could provide an oasis, literally an oasis in the main asteroid belt for exploration. We're also doing a bunch of internal risk reduction tasks for both options, the deployable bag that you saw in the animation and the robotic system for option B. And I'm running a little bit short on time, so I'll just say that we've looked at different operations and different configurations for the option B, and I've been leading the studies here at Langley in that effort here locally in Virginia. I've got an animation that shows the process. ARV, we're trying to take what we call a modular approach. Just like a tractor trailer has a cab and the trailer, to be able to break it apart, we want to be able to have a spacecraft that we can use for other missions, like slow boating material around the solar system. So we've got this SEP module and a mission module, and those form really a spacecraft bus. You could do what you want with it. You could do a scientific mission, you could push a habitat or a lander around, push some fuel somewhere, but we have this capture module that we would put on the front for either option, and then you have some sort of common interface so you can put other types of modules on it. So one of the things we talked about was the ability to do planetary defense demonstrations when we're at the asteroid. And I think this is really a very important and a key aspect of this mission, in addition to the exploration value and the resources. We can demonstrate, we're planning for option B to demonstrate what we call an enhanced gravity tractor. So gravity tractor it uses Newton's laws, and you kind of saw in the video in the animation. Just go into a halo orbit around and station keep with the asteroid. You can stand off or you can go into an orbit, but as the asteroid's turning, the spacecraft is just there. And the two actually attract each other very, very minutely, but it's enough that if you can hold the spacecraft in one position, it literally is a gravity tractor beam that will move the asteroid. Now, the bigger the asteroid, the harder it is to pull. But of course, you can, just like a team of horses, you could actually put multiple spacecraft in that orbit and pull and provide more of a force on the asteroid. And what we're talking about doing in option B, is going down to the surface and actually picking up a boulder off of the surface that's many times heavier than the spacecraft. Now we've got this more massive spacecraft in orbit, and that amplifies that tractor beam effect to the point where it may take, for a very large asteroid like Itokawa, it might take 100 years or more for that spacecraft to move it enough to make it miss the Earth. With a boulder or material, you could collect a boulder, or you could scoop material in the final planetary defense mission. If you could get about 250 to 300 tons of material off the surface, you could move that same asteroid in about 3 or 4 years. And if you had multiple spacecraft, you could do it in just a couple years. So there's a lot of power in that ability to go down to the surface and get mass. We can also use the ions that actually come out of the thrusters to actually hit the asteroid and literally push it with the exhaust. And that's another technique, and the big advantage of that is you don't have to touch the asteroid. You don't have to come anywhere near it. Another technique that's called a kinetic impactor, we can also demonstrate with option B. We don't have that in the baseline program right now because of the additional cost, but basically the ARV would watch as another spacecraft came in and impacted the surface, and then we could measure and see what the effect of that was. This is probably the most viable short-term technique in the planetary defense system or set of techniques that we could use. Another one is surface ablation. That uses a laser beam, kind of like the ion thrust hitting it, but now you focus a laser beam on it, you burn off portions of the asteroid, and that causes a momentum change. And I could talk for an hour on all of these, but we don't have another
Yes, he
hour.
can.
So,
he does it every night on the drive home from work.
Yeah. So I don't know how to respond to that one, because he's right. But I'm just going to close with this and turn it back over to Pat to finish up. There is a distinct connection between the threat that asteroids are, the hazard. I don't like to use the word threat because that kind of makes them sound like an enemy. They're just doing their own thing. They're not trying to hit us. We just happen to be in the wrong place at the wrong time. But the asteroid hazard is also combined with what I talked about, that economics of space. They're a valuable resource. They may have everything from water, which we need, to metals, platinum metals that we may need on Earth someday. Hopefully we never have to import water from space, that we can manage our resources in that manner. But there may be materials on asteroids that we have never seen before because of the conditions, the microgravity, and the conditions that they're created. So there's a lot of potential there. And I'll just close with what I think is kind of a key aspect is, right now we talk about planetary defense, we're talking about doing techniques, but we don't have a dedicated planetary defense system. It's a very infrequent hazard. You know, it could happen tomorrow, but not that we know of. We don't know that there's anything on a collision course. But for example, Comet 2012's A1 Siding Springs is going to make a close pass by Mars in October of this year. So close that we're taking, the NASA agency and other international partners are taking precautions for the satellites that are in orbit around Mars to make sure that there's no effects from the comet. But you've got a fairly large body coming in that we just found, 18 months ago or so. And so there's the ability to have kind of an integrated solution. And the analogy that I give is bulldozers for snow plows, okay? You need snow plows to plow the roads during a snowstorm, right? It's a natural hazard that we have to deal with. Problem is, if you try to sell snow plows to, say, the Tallahassee city municipal government, they're going to go, we don't need those. We've never had a snowstorm like that. Well, not in the recent past, but there actually has been snowfall in Tallahassee. If the climate changes, we could have a change in the weather. But you can sell them on bulldozers, right? You can do construction, you can be productive, and in a pinch, you can turn those bulldozers into snowplows if you ever had this blizzard come along. So it's that idea of leveraging the capabilities that we have for human exploration and for mining the resources of asteroids that could one day help us with the planetary defense aspect as well. So there's opportunities and extensibilities for the asteroid mission, in addition to planetary defense, the science, and the extensibility. So again, the Mars forward path, and I'm going to turn it over to Pat, is what the asteroid redirect mission helps us focus on in the near term within the budgetary constraints that we have at this point. And with that, I'll give it to Pat for the closeout.
You went longer than me.
I was supposed to go long. I was supposed to go longer than you.
All right. So we started at NOVA. We went back to low Earth orbit. We progressed through geospace. We've gone to cislunar space. We've gone to asteroid. Our next step along the path to the future is Mars. Mars is a good candidate for establishing a human seed someplace else. It has abundant resources on its surface. It has glaciers of water. It has all the natural materials. It might be hazardous to human life. We're not sure about that. That's why we have to go check it out with some of our robotic missions. Huge problems in getting there, Steve mentioned. Getting to the surface. Mars' atmosphere is very, very thin. It's like being at the top of Mount Everest or something worse than that. Its gravity is 1/3 that of Earth, so it's twice as much as the Moon. So parachutes don't work well, and if I'm using rocket engines like I'm doing to get to the Moon, because there's so much more gravity, that doesn't work too well either. So we're sort of stuck somewhere in between. So you're getting a big lecture on that. So it's hard to get to the surface. That requires a leap in investment and capability. But that leaves other things. There's the Mars system. Now, for the sake of time, I'm going to skip this entire section. Dan did an excellent job of talking about how we use solar electric propulsion to get there. So I'm going to summarize the next 3 slides in this one. If you look at this chart, and you look at the little things where the thrust's coming out of, those are basically 2 of his vehicles that he uses to go get an asteroid. If you look at the big solar arrays on there, they're much bigger than his because Mars is farther and harder, and we're taking people there and back, and they're a lot heavier to get there, not heavier coming back. So there's a big good synergy, as Dan mentioned, between how we get people back and forth to Mars and what we're exploring with this asteroid redirect mission. By the way, this vehicle is fully reusable. You fill it up in cislunar space, it takes the crew all the way to Mars, everything comes back, gets refurbished and reused in cislunar space. We're not throwing away things like we used to do. This is not Apollo, because if we're going to go beyond the solar system to Nova, you need spaceships that last a long time and are reusable. So this is what we're trying to infuse into our architecture. So another course, we'll talk about this. But let's talk about what you do while you're waiting to get to Mars' surface. Does everyone know that Mars has 2 moons, Phobos and Deimos? Some people think they're captured asteroids. Some people think they're a part of the creation process of Mars itself. The answer is we don't know. Almost everything we know about those 2 moons is captured in these pictures. We got pictures. We got some spectrometry. We never sent a probe there. The Russians have tried to send 2 probes there. Each one has failed. But they offer such a unique platform. Because you can land on these, they're very, very micro-G bodies. You can use the bodies themselves to protect you from the galactic radiation that we have in space. So we solve part of the radiation problem by actually going to these moons or the surface of Mars. But these again, are a lot easier to get to. So one cool thing about them is that, as I said, they're micro-G bodies. So me with a spacesuit on, I would weigh 0.3 pounds on the surface of Phobos. An entire 50,000, 100,000 pounds in English units weighs 63 pounds. So moving around these planets is incredibly easy to do. So basically, if I were on the surface and I did this, I could go 6 or 7 miles.
In 1 leap.
And I'd do it slowly. In fact, if I did it well enough, I would go into orbit and I would leave Phobos and go into Mars orbit. But what that buys you is the ability to navigate, to explore with very little energy, very little propulsion. You just have to be careful. So what you see in the bottom here is an engineering sim showing going from, there's a large crater called Stickney Crater, and it's this big place that looks like someone took a shotgun to it. There's a habitat in there, and they're doing a 30-minute commute, the same time that Dan and I go back and forth from Williamsburg to Hampton. They go miles in this air. So they just did a hop, basically a 4-meter-per-second hop. And they're flying up. They're going over from this side of the moon to the other, and they're going to fly over this crater rim. See the little shadow down here? They're just going to get close to the crater rim, and as they get to the crater rim, they're going to skim on by it, and you'll see the shadow fall away. These are very daredevil-type pilots. Now, here's another view. This is the Hollywood view, they call it. There's the habitat down the bottom of the crater. It gives you a rough approximation scale. And there's the vehicle that actually flies. It looks like a little bug. All it does is it pushes with its legs, and it does a little thrusting. And there it is, shooting right over the rim of the crater. And lo and behold, what is this thing you see here, coming up here? Have you guys heard about the monolith on Phobos? That is actually to scale. It's about 100 meters tall. And it's this big rock thing sticking out the surface. We don't know what it is. It could just be a rock that hit into the moon and landed sort of funny. It could be something from Space 2001. We just don't know. So there's abundant science there on Phobos and Deimos. In fact, impacts on the surface of Mars from asteroids throws up regolith, and so there's pieces of Mars on Phobos. 50 million years from now, Phobos is going to orbit, is going to decay. It's either going to break up or it's going to impact the surface of Mars. Maybe we want to know what's going to happen to Mars. Understanding Phobos is going to tell us that. So lots of good reasons to go there. Lots of cool ways to explore. So that's why the moons of Mars will be our next step. We're not going to go direct to the surface. We're going to go to the moons of Mars, stage ourselves, get ready to go to the surface, operate robots on the surface of Mars while we're in the moons of Mars. So that's the next step. So we figured, Dan already talked about this. This is how he pointed it out. There's the Mars, the Phobos vehicle. There's the asteroid vehicle. This is early 2020s. This is mid 2030s. It look about the same. So again, we're investing to go multiple places. Mars, the way you want to do Mars is a sustainable way. So we're rethinking Mars. Before, in the last couple of years, we've been thinking Mars missions where we go down, we do some science, we bring out some rocks, and then we never come back to that site again, and we throw everything away. That's not extending the human seed. So we want to take advantage of the resources on Mars, go to the same spot over and over again, build infrastructure, extend our presence. But that's child's play, because the next place you want to go is the Jovian system.
Can I ask a question? We're running out of time. You said you were going to do.
Yeah.
Quickly, yes.
And continuing in this scenario, let's make believe I'm King Ferdinand and you're Chris Columbus. Chris, you said before you had a budget. So how much money do you want?
Okay, so you can't quote me on this, but I did see some budget analysis today that said if we were to terminate space stations before 2028, we would have enough budget within existing NASA guidelines to go to Phobos in the mid-2030s.
I'm King Ferdinand. You're asking me for money. You want to go someplace. How much? Give me $1. Give me
The current NASA budget for human spaceflight, $8 billion a year. That's the current NASA budget, $8 billion a year. I was just trying to get there. And that includes the launch vehicle development and everything else. That's current. From now all the way to the surface of Mars. So what is that, 20 years from now? That is 20 times 8, $160 billion. And if we don't go anywhere, it's still $160 billion because of the political aspects of it. So we want to take that $160 billion and do something good with it. Okay? And so now, let's talk about 20 years beyond the surface of Mars, Jovian system. Dan showed a video where the sun turns into a red giant. Eventually, if that ever happens, it's going to actually start getting warmer and rather nice in the Jovian system for a time. The Jovian system is full of hydrogen and water. It has moons, Callisto, Ganymede, that are all made out of ice and water. So what you're seeing here is little animations of mining ice and using it as a waypoint to go to future destinations in combination with the asteroid belt and other resources in the solar system. Dan showed you configurations where we had kilowatts of power to push these things. We need megawatts of power, nuclear in-space power or some magic fusion or something like that comes along to get to this point where we could go back and forth to Earth and power these large solar system class spacecraft that have rotating sections and the crew buried in hydrogen tanks to protect them from radiation. You have to go the next step because the journeys are long, even with all that power. But that's an interim step to what we're talking about here, which is other solar systems. So we stay small low Earth orbit, we progress our capabilities, we get to the point where we're going from years to decades and centuries in travel. And so we want to end up where we started, that right now, as a civilization, we're pretty at our peak from a technology perspective. We can argue politics and social and stuff like that. Technology, we're really, really, really good. There is enough financial means in the world, applied properly, to begin doing this. We don't need budget increase, we need budget redirection, budget focus. But as we all know, this window doesn't last forever. Crises happen, Ebola, whatever it is. And this is something that, as we've shown, takes decades and generations to actually accomplish. So if you say, well, let's wait until the killer asteroid comes, or let's wait until a million years before the sun goes red giant, it's going to be too late by then, because maybe we'll pass through this opportunity we have right now. So one day we have to leave the cradle. You can't stay it forever. So I think our point is that this is how we'd like to proceed. This is our plan. This is our strategy. And with that, we have
a few minutes
2
for
minutes
questions.
for questions. Yes, sir.
How do you know life is going to be more sustainable on Nova or wherever it is you go?
We don't. And in fact, I pretty much say that any natural disaster that happens on Earth will still be the most habitable place that we know of. It still will be. However, if the decay of civilization, Earth still may be more habitable, but civilization might be at a better peak someplace else because of having the cross-pollination. So you're right, NOVA will be if we send a probe out there, we're not going to know. But remember, we're going spaceships that have kept people alive for 200 years. So if it's a bust, you're just orbiting NOVA or extracting resources of that to figure out another planet.
Yeah, let me just add, we're finding more and more planets every day. I mean, literally, we've got more advanced telescopes. One of the aspects is, if we find the right planet, okay, again, red giant, sun stops sustaining life, that's probably billions of years. But orbiting a red dwarf, as actually NOVA does, it is a much longer-lived star, tens of billions of years. So there are different classes of stars that have longer lifetimes. If you find the planet, what they call in the Goldilocks zone, the right place where liquid water and the right temperatures can exist. It's finding it.
What's wrong for them to use the word indefinite?
Well, yeah, technically indefinite, there's no such thing, right? You always have to move from one solar system to another in the big scheme. Yes?
You talk about it takes a long time to get to the outer space. Well, what's the minimum age when you send them up there?
Well, and this is why the pictures that we showed here, these are big self-sustaining arcs. These are generations that are living during the generation. Now, the good news is that the older you are, the better you are as a space candidate, because the bad implications of radiation only impact you 20, 30 years after you go. So statistically speaking, older people going have a less chance of developing cancer and bad things because they'll pass before they actually take impact. So we always say the ideal astronaut candidates are women from Nepal who are already red hard, who are senior citizens. They're perfect to send to space.
Yeah, but to add to that, Pat's talking from an astronaut standpoint. I wanted to be I wanted to be an astronaut at one point, and that's never going to happen. I'd like to see space opened up to all of us. And that's going to happen through commercial endeavors, et cetera, just as everything has happened. I personally think one day we will colonize the moon. And I would love to see, if before I retire or after I retire, I'd love to see a retirement community on the moon. You think about how you would react in 1/6 gravity. You wouldn't have all of the issues. You could go out and play golf, play basketball.
Everyone hit a 500-yard drive.
Everyone hits a 500-yard drive. So space is for everybody. We just have to find the right way to get it open.
We're at the explorer stage, and the explorers were the rough guys and they knew the risk was really bad. We're trying to get transitions for explorers to pioneers. And that's the different mindset right now, is that actually you want to get to the point where everyone can eventually get there going. At least a larger... Right now, we have 6 astronauts in space. That's 1 out of a billion people on the world get to go to space. We got to up that ratio a little bit.
When you bring them back, they're all shrinkled up.
Is there any other questions? Oh, yeah, back here. Yes, sir.
2 questions related. If you are looking for another location somewhere in the universe, what is the likelihood that if you find something that you expect to be habitable, that it isn't already inhabited? There aren't life forms of various types already there.
Very possible. Okay, so again, right now we don't have any proof that there's life beyond the Earth. That's just the fact. We haven't discovered it yet. My personal opinion, the galaxy, the universe is probably teeming with life. So you're absolutely right, and we try to kind of avoid that question. It's probably an entire philosophical discussion to be had.
Well, in fact, we're worried about Mars.
Yeah, and Mars itself. There could be microbial life on Mars. How do we deal with that? Okay, that's a big question, and we need to start talking about that and learning that now so that we're ready. Typically, what happens is whoever is exploring and colonizing adversely affects the life forms that are there.
And vice versa.
And there can be vice versa.
Yeah.
So,
as history has shown.
But when it comes down to it, in terms of survival and extension of human and other species on Earth, that's where there's a philosophical discussion about it. And hopefully you can find a planet that's that's not inhabited, or that you can share that planet, that's something to be talked about.
And frankly, you probably will not know till you get there. That's the sad part.
Yeah, or we can, I mean, they're already talking about sending probes to planets in other solar systems. It's going to take a while with our current technology to actually get there, but, you know, eventually that's what we would probably do. Thank you all very much.
Thank you, guys. That was great. I hope everybody is now interested in where we're going in deep space. Next week will be Orion, and so hope to see you here.